I want to start today by reminding you of the definition for what it means for a sequence to converge. Right? So we say that the sequence A sub n converges to L, or has limit L, if for every epsilon bigger than 0 we can find, or I guess I should be more specific, there exists capital N such that if little n is bigger than or equal to capital N, then the sequence members are within epsilon of L. Now we've gotten some experience using this definition. We've proved some theorems using the definition. But it's time now to highlight a weakness of the definition. And that is this part here. Right, if we want to prove that a sequence converges using the definition, then we have to actually know what it converges to. Right? So most of our exercises have been find the limit and then show that the limit is what you say it is. But there are lots of sequences for which it's not easy to find the limit. You certainly can't know it just by looking at it. And if you can't figure out what the limit is or don't know it in advance, then proving that it is the limit is hard. So to use this definition requires knowledge of what the sequence converges to. And of course there are lots of sequences for which we may not have that knowledge. And that is where the material of the current sections comes in very handy. So what we're about to do is present an alternate property of sequences called the Cauchy property that allows us to know when a sequence converges, but crucially, it allows us to know that even if we don't know what it converges to. So we're going to now present this idea of a Cauchy sequence, and the rest of the work, and there's a fair amount of it, is devoted to showing that if you know a sequence has the Cauchy property, then it must also converge. What's missing is that in the Cauchy property, you don't have to know what the sequence converges to. So it's a really important property. It'll be especially important when we talk about infinite series, when we want to know if an infinite series converges, and we want to be able to answer that even if we don't know what it converges to. So that's what we're about to do. And I'll remind you of the definition for a Cauchy sequence. It looks similar to the definition of convergence, but the idea is certainly different. So a sequence A sub n is Cauchy if, so we start again with any positive real number epsilon, which we typically think of as a small positive number, but can be anything. So if for every epsilon bigger than 0, there exists some capital N, which likely depends on the epsilon, such that if m and n are bigger than capital N, so m and n are two indexes for the sequence that are both far enough out in the sequence, then we have the fact that the terms in the sequence are within epsilon of each other. Right? So that's a distinction between the definition of convergence and the definition of Cauchy. In convergence, we have a known limit, and the sequence has to get as close as we'd like to that limit. In the Cauchy definition, we don't have a known limit, but we require that the members of the sequence get as close as we like to each other. So this property of getting close enough to each other you can think of as requiring that the sequence kind of bunches up. And that sort of bunching gets tighter and tighter as you go further and further out in the sequence. And if we think about what that might look like with the sequence members getting closer and closer together, you can kind of picture that that also seems to indicate some kind of convergence. So if we had a picture, won't necessarily be a very good one, as always. So we have some sequence on the real line. And what we're saying is that eventually the members of the sequence can't depart from one another very far. And if they bunch up that much, then it looks like there ought to be some capital L in there to which the sequence is actually converging. And we're going to show that that's in fact true. So our big theorem for this material is the Cauchy criterion. And that is a sequence is Cauchy if and only if it is convergent. So if you know a sequence converges, it's automatically a Cauchy sequence, and if you know a sequence is Cauchy, then it automatically converges. And our work is going to be to prove this theorem so that we can then use this Cauchy property as a way of telling when something converges when we don't know what it converges to. So we have two directions with an if and only if. One is, well, let me just sort of outline where we're headed. Direction one is convergence implies Cauchy. We're going to see that that is by far the easier of the two directions. That if you assume convergence, it's not hard at all to show Cauchy. Because if you assume convergence, the members of the sequence get as close as you like to some capital L if you go far enough out in the sequence. But if you're that far out in the sequence and everything is within epsilon of capital L, they're also close to each other. Right? So, there are a couple of details to sort out, but that's roughly how that proof is going to go. The harder and more interesting direction is that if you have a sequence that's Cauchy, it's also convergent. So I had a undergraduate writing professor who, one of the things that stuck with me from his classes was that his saying for fiction writing was that only trouble is interesting. So that if you're trying to write something and you want to capture the reader's interest, there has to be a lot of trouble in your story. And that applies to math as well. So the only results that are sort of mathematically really interesting are the ones that aren't obvious, right? So this is one that's not obvious, that Cauchy implies convergence, presents a lot of trouble, right? So mathematically, this is the more interesting of the two directions, and the rest of our work is going to be to show it. We're going to have to do this in a series of steps. The first is going to look like Cauchy implies bounded. So any sequence whose members bunch up together eventually has to also be a bounded sequence. We'll prove that. Next, we'll show that all bounded sequences have a convergent subsequence. That is a big part of our proof. This is a difficult step, and you sort of know that it's difficult because it has its own name. The fact that all bounded sequences have a convergent subsequence is called the Bolzano-Weierstrass theorem. So that is one that we're going to have to prove along our way to showing Cauchy implies convergence. And then the last piece will be that if you take the subsequence guaranteed by the Bolzano-Weierstrass theorem within your Cauchy sequence, the Cauchy sequence has to converge to the same thing as the convergent subsequence. So the Cauchy sequence converges to the same limit as the subsequence that's guaranteed by the Bolzano-Weierstrass theorem. All right, so to recap where we're headed, we want to be able to prove that a sequence converges even if we don't know what it converges to. That's why we need the Cauchy criterion. So instead of focusing on getting close to L, we focus on terms getting close together. Then we show that really being Cauchy and being convergent are equivalent. So we have to show convergence implies Cauchy. That won't take very long. It's fairly straightforward. But then the direction that presents the trouble, so presents the interest, is that if you know a sequence is Cauchy, it's also convergent. And that's going to occur, the proof of that occurs in 3 steps. First, we show if it's Cauchy, it's bounded. That's fairly quick. The biggest step is this one, that if you have a bounded sequence, it has a convergent subsequence. That's the Bolzano-Weierstrass theorem. It has a really, really clever proof. It's a really cool proof. And then finally, we show that the subsequence that Bolzano-Weierstrass gives us converges to the same limit as the original Cauchy sequence. And then we will have proven that Cauchy sequences converge. So that's what's coming in the next couple of videos.